All right, good day, everybody. Can you hear me and can you see my screen?
Yes, sir. Good morning, sir. Yes, you can see.
All right, thank you. All right, let's just take a few seconds to scan your attendance and we shall begin with our class again today. All right, let's begin our class today. All right, good day, everybody. Welcome back to our class today. And yep, before we begin our class today, all right, if you have noticed in the our chat, our Teams group, so I've made an announcement this morning. So if you missed the announcement, here it is. So we are right now at the end of our semester already. Oh my God, look at how fast time flies. So we are going to be having finals in a few weeks' time, right? So I was thinking that because I'm preparing your carry marks right now, and I noticed that some of you have not completed some of the assessments. So I am giving everyone like a fair chance once again to complete all your submission as soon as possible. So the cutoff date for the submission is going to be 12th of December. And the reason I need to have this cutoff time is because I need to prepare your carry mark before that time, right? And once I really hope that I can release your carry mark by the end of next week if everyone submits on time, right? So I will not accept any late submission because like those are late assignments. I believe you have the entire semester to complete it already. So hopefully those who have, if you intend to still submit your assignment, please do so as soon as possible. Please do so by 12th of December before midnight. And if you do not intend to submit, like it's okay, you don't have to do anything, all right? So if you have any questions, let me know. Hopefully that is clear. And this week we are actually, this week is going to be the last lecture. Actually, this lecture is going to be the last lecture. Okay, not last as in I'm going anywhere. Last lecture for the semester. So I would like to congratulate everybody for staying up to this point. Like in the last semester, like I noticed that halfway through semester, 3/4 through the semester, there are students who are dropping out already. But this semester, I didn't notice that yet so far. So congratulations for making it through this semester again. And I realized also that this could be, I think next semester, you guys are going back face to face, right? I think no more mixed alternative assessments. I think next semester onwards. So I think you guys are like the few lucky ones who are able to like go through take the entire semester with alternative assessments, because I know like exam sucks, right? So exams like it's gonna start back next semester, but it's okay. All in all, thank you so much once again for enrolling for this class. Let's continue with our class again today, and I really hope to finish our last topic today. So today we are going to finish. Let's see. Let's go back. So this topic is the last topic in your course outline, and it's a topic that is very related to our last topic. In the last topic, we've talked about flip-flops, right? And we talk about latches, right? So far, in in flip-flops and latches, you guys have not yet seen what are the practical use of this thing. Realize that all you've done so far is like, okay, give me the truth table, give me this table, give me that table, and like everything is just kind of like memorizing. And I know like memorizing is not a good way of remembering for long term. So this chapter is going to make sure you solidify that knowledge of flip flop and latches, right? So one of the most fundamental use, one of the most direct use of flip flop is when we design counters. Now in this chapter, this entire chapter, we are going to dedicate just to design counters. Okay, all right, and no doubt there are a lot of other things that you can design. You can use flip flop for, but a counter is like one of the most straightforward example. And it once you know how to design counter using flip flops, like pretty much you can design other things, and that unfortunately we don't have enough time to cover for this course. Well, I really hope that after this course, after you've done with this digital logic, I really hope you guys can just explore what other uses of flip-flops there are out there, and there are a ton of them. All right, so let's get back to chapter 8, counters. It's a very short chapter. I think we're going to finish in like no time, maybe less than 1 hour. So I really need your attention on this chapter, and then we'll end the class already. All right, let's take a look. All right, so just a little bit of introduction. So in the last chapter, we've learned about flip-flops, right? And what we've done in the last chapter is we've learned flip-flops individually. So we've talked about SR flip-flop. We've talked about how SR flip-flop work. We talk about how JK flip-flop work. We talk about how does it, what kind of a mode. Remember, there's like 4 kinds of mode. There's no change mode, there's toggle mode, there's what are the, there's set and reset mode, and so on and so forth, right? So those are individual flip-flops performing their one function only. And frankly, like I'm not sure how many of you noticed, it seems to me like it's pretty useless. Like those flip-flops, they function on their own. So what if it's toggle mode? So what if it's no change mode? So what if it's reset mode, right? So by itself, it's very, there's not much use of it. But if you combine them together, if you arrange them in a very specific way, it can perform kind of an intelligent function. One intelligent function, kind of intelligent, is this counter. So we'll take a look at how this can be arranged to perform this counting function, right? All right, so over here, flip-flop can be connected together to perform counting operation. So these are called counters, right? Counters. So what exactly is counter? So the name is very kind of straightforward, but I guess I better clarify things a little bit. So counter is something like a stopwatch. So if you have a stopwatch, so your stopwatch starts at 0, right? 0, 0, 0, 0. That's how your stopwatch the default value, right? When you start. So after that, the next value will be 0, 0, 0, 1. Okay, let's say 1 second. So it goes so on and so forth. You start from the value 0, and then you go to the value 1, and you go to the value 2, and then 3, so on and so forth. And up to one point, when you decided to stop the counter, you can go back to the value 0 if you want. Okay, so this is how a counter works. And in this counter, it counts up. It starts from 0, it goes up 1 value, it goes up 1 value, right? Goes to 1, goes to 2, 3, 4, 5, and so on. So because the value is going up, we call this a up counter. So I would like you guys to notice the keywords that I'm saying over here, because why? These keywords are key for you guys to do your own research. When you come across this keyword later on, when you do a research online, then you know that, oh, up counter is that thing that I mentioned in the class, right? So do notice these keywords. So I purposely put these keywords like over here so that you can notice them. There is up counter. There is also a down counter. Okay. Down counter. Okay, so down counter does the reverse, right? It starts from a larger number, maybe 10, and it goes down 9, 8, 7, 6, 5, 4, 3, 2, 1. So those are down counter. Okay, right. So up counter can also be in a slightly different. It can behave slightly different way. Instead of counting from 0 to 1 to 2, it can also make the counter do like 0, and then to 2, and then to 4, and then to 6, and then to 8. Okay, and then after that, it goes on to reset the value back to 0. So this one is also an up counter, but this counting happens in a different fashion. So in this case, it's like 0, 2, 4, 6. So the same thing with the down counter, right? And the thing is, you can design using flip-flop, you can design any kind of counter you want. Okay, you can design a counter that does strange counting, like 0, and then 3, and then 5, and then 2, and then 4, and then 8. You can design it in that way using flip-flop. So this topic is all about designing that. How do you use flip-flop to design a counter? It can be this up counter that counts from 0 to 10 and then resets, and it can be a down counter. It can be any strange counter you want. You can design a counter to count your ID card number, for example. Okay, that's a hint. That's your project. Talk about that later. So in this course, in this last topic, we are going to see how we are going to use flip-flops and arrange them in a very intelligent way to make this sort of counter. All right. So first takeaway today, counters, we have two types. We have first type is called the asynchronous counter. Okay, asynchronous counter. Second type is called the synchronous counter. So almost the same name, but the function is very different. Okay, of course they still do the counter function, but the way it is arranged, the way it works, it is different. All right. So today we are going to I'm going to show you guys on how asynchronous counter works, and I'm going to give you a homework to everyone today to figure out how synchronous counter works. Okay, so this I hope you're beginning to see a trend over here. In the beginning of the semester, I spent a lot of time with you guys. Remember, on topic 1, topic 2, I covered pretty much every single point in the topic, just so that you can have a very good understanding, very firm fundamental understanding. All right, that was done on purpose. I didn't and as we go on gradually, I give you more freedom, and during the midterm I give you the freedom to do some kind of a research project. And then after that, topic 6, 7, and 8, I give you even more freedom. Like the homeworks are becoming more and more open-ended, and you guys have chance to make your own circuit, make your own implementation. All right, and you guys have had chance to play with some kind of a tool. Remember, circuitverse and logic.ly. So those are the tools that I hope you guys have made use of. And as we approach this last topic, this topic is going to be a very open topic. Okay, it's a very open topic. It's a topic that gives you the most freedom. And instead of holding your hand, like just I did, like just we had in the last few topics, topic 1, 2, 3, and 4, this topic is going to be very free. I really hope that you guys can appreciate this freedom. And what do I mean by freedom? So the freedom is over here, the freedom to do your own research, to do your own study. And the reason I think this is useful is because, as I have been saying in the class, this knowledge in digital logic is too much for us to study, for us to cover in the class. So what I'm trying to do right here, especially in this topic, is to give you points, to give you keywords, to give you the fish, so you can use this and expand on that knowledge. Okay, because I really have we don't have all the time in the world to cover every single thing. In fact, every day new things are being added into digital logic, new discoveries are being made. So what the best I can do is to equip you with fundamental knowledge so you can use that and learn all these new things. This is, I think, the core of what I'm trying to do. This is this main thing I'm trying to do with this course. So don't just remember what I'm telling you in the class, asynchronous, up counter, down counter, but use that as a fundamental to learn something more. Okay, in this case, I am giving you another homework over here to learn about synchronous counter at the end of today's class. But before that, as promised, I am going to give you all the information and all the keywords that you need by covering asynchronous counter together in the class, right? It's going to be a relatively quick one, but I need your attention right now. Let's dive into asynchronous counter and see how it works. Okay, so asynchronous counter is it's counter, and it's got a funny name over here, asynchronous counter. All right, so over here in this diagram below, I am showing you this simplest form of an asynchronous counter. Okay, let's break this diagram down. Okay, so over here we have flip-flop, we have flip-flop A, and we have flip-flop B. Okay, and in this case, what are the flip-flops? It's a JK flip-flop. That's why it's written in that way, right? So if you see diagrams online that looks like this, then you know that's how you break these diagrams down, right? So I'm teaching you guys how to read this diagram first, and then we'll take a look at how it works. So if you see this diagram in your research in using synchronous counter, yes, this is exactly what it means, right? So flip-flop A, flip-flop B, JA stands for J input for flip-flop A. This is K input for flip-flop A, and same thing over here. We have J input for flip-flop B and K input for flip-flop B. Okay, that is just the name to distinguish between the two flip-flop. Nothing fancy at all here. Same thing with Q. We have in a single flip-flop we have Q and Q bar. Over here we have Q A to distinguish that this belongs to flip-flop A, and the other one belongs to flip-flop B. All right. So the rest are pretty much the same. So over here we have a clock signal. You have a clock signal over here. All right, so that is two different flip-flops. Now let's see how is it connected. Right, take a look at how is it connected. Let's take a look at J and how is it connected. It's connected to a high signal. Okay, and K over here also, it's connected to the same high signal, right? And let's take a look at the other one. What about this next flip-flop? Flip-flop B, JB is connected to this high signal also, and KB is also connected to this high signal. All right, so what does that mean? So if you remember in the last class, this is a JK flip-flop. So what happens if you have a JK flip-flop that has both inputs to be high? What mode is this in? Okay, this is in the last mode, which is the toggle mode. Let me not write here. Let me write. Okay, toggle mode. Okay, that's one thing to take away over here. You have JK flip-flops. They are both connected to a high. High means logic 1. Okay, logic 1 signal, and that puts this flip-flop into a toggle mode. Toggle mode means it's going to flip whatever input that it has. Right? That's all. All right, that is the input to JK. Now let's take a look at this the input for the clock signal. All right, so let's take a look here. Let me change this color. All right, so take a look. This flip-flop is a rising edge trigger or a falling edge trigger. So the only way for us to know is to look at this signal over here. If you got the bubble like that over here, you know that this is a falling edge flip-flop, but in this case, we do not have that. Right, so this is the clock signal coming from outside another input, and it goes to this first flip-flop. All right, so what about the second flip-flop? Take a look at the connection of the second flip-flop. So the connection of second flip-flop is actually a bit strange because it does not come from the clock over here, but it comes from the output of the first flip-flop. And it comes from the Q bar output of the first flip-flop. Okay, that is kind of strange, but you'll see in a minute how it works, right? So the green and the red, they are not connected. Okay, that's why I'm using different color. All right, so QA and QB is the output signal. Okay, we'll take a look at how QA and QB works. So if you take a look at this, now I hope you're beginning to see why is it called asynchronous counter. Okay, and another name for asynchronous counter is called the ripple counter. So why is it called a ripple counter? Because you see that the input goes through the first flip-flop first, and then that output of the first flip-flop ripples to the another flip-flop, and then if you have more flip-flop, it's going to ripple to the next one and ripple to the next one. Okay, it's going to be like a wave. The output for the first one, wave ripples to the second one, ripples to the third one, ripples to the fourth one, and so on and so forth. Okay, so this is called a ripple counter for that reason. Okay, if you don't like this name, asynchronous counter, you can just call ripple counter, same thing. All right, so in this ripple counter, this is the simplest of ripple counter. This is a 2 bits asynchronous binary counter or a 2 bits ripple binary counter. So why is it 2 bits? It's 2 bits because it's got 2 outputs, right? So where's the first output? Let's take a look at that. The first output would be QA would be output number 1, first output. Okay, QA is the first output, and this one is the second output. Okay, all right. So this is 2 bits. So you can have a ripple counter that has more flip-flops, right? If you put in one more flip-flop over here and you connect it just as like we did in the second one, you'd have a 3-bit ripple counter. If you add one more, you get 4-bit, 5-bit, and so on, right? So that is adding on building blocks, but they are the same thing. So we are going to talk about the simplest one here because I believe that if you can understand this 2-bit counter, I give you 3-bit, 4-bit, 5-bit, you have no problem understanding that as well. So let's get the fundamental right over here. Okay, this is a 2-bit counter, and this thing to note is over here, the first one, the clock is only given at the first flip-flop only. Okay, this is the first flip-flop, right? And the second flip-flop is triggered by this QA. So this is what we were talking about just now. The clock to the next flip-flop is triggered by the output of the previous one. So that is how a ripple counter works. All right, so that's how it's arranged. Now let's take a look at how it really counts, really. So I'd like to draw your attention over here. So let's take a look at this very simple table. So initially, for all flip-flops, we need to have an initial state, right? Remember, in the last topic, we also talked about initial state for a flip-flop is important because that is the present state, present condition of the flip-flop. It's important to know the present condition because a flip-flop will take the present value and then either flip it or keep it, or you can set or reset it. Okay, so you need a present value. You need an initial value to the flip-flop. So in the counter also, same thing. We need an initial value. We need a present value. So in many cases, usually we will assume that the flip-flop is initially reset, okay, or initially it's this value 0, 0. Okay, so QB and QA, they are both 0. That is our assumption. Okay, we can of course, like the question can change. Like initially you can assume it to be 1 like that. It's also possible, right? But I'm not going to do that. Like let's just keep it simple. Initially we assume everything is 0, and then let's see how this thing counts. All right, let's take a look at this timing diagram over here. So this timing diagram is simple. First row on top, we have the clock signal. Second row, we have the output. Okay, let's just take a look at how this thing works, okay? So this timing diagram, okay, obviously it's from the left to right. Okay, forgive my crooked line. So let's just walk through step by step in the timing diagram. That's how we interpret the timing diagram, okay? All right, let's take a look at in the beginning of time, we assume that everything is 0. So over here is 0, right? So QA is 0, QB is 0, and even the clock is 0 in the beginning. Right, so let me just write this real quick. 0 and logic 0 and 1. I'm just trying to show you here. Okay, so what happens if we progress through time, right? Let's just traverse through time, and at one point when the clock signal becomes high, like has a rising edge over here. So what happens? So when we have a rising edge at the clock over here, which flip-flop will be triggered? So the flip-flop that's connected directly to the clock is this guy over here, right? So then, if you have a rising edge at this clock, at this time over here, this is going to trigger this first flip-flop to be on. Okay, now flip-flop turns on, and then once it turns on, it's going to see what mode is this in. So what mode is this in? This is in the toggle mode. Because why? Because J and K, they are both 1s, right? They're both connected to high. So this flip-flop is going to see, oh, this is in toggle mode. In toggle mode, what it's going to do is going to take the existing value, whatever you have right now, and flip it. Okay, that is what happens over here. This flip-flop turns on at this point. Okay, turns on at this point when it's got triggered, and it's going to take the existing value over here. Existing value is 0 because we assume that everything is 0 in the beginning, right? It's going to take that value and flip that, and it turns this into a 1 over here. Okay, from 0 it becomes a 1 at this trigger point. Okay, the vertical line is the trigger point where the clock gives you an edge. So that triggers that output to be 1. So this is Q, right? So now Q becomes 1 over here. Okay, and Q becomes 1, and then we have right. So we have one more output here that I didn't draw on this diagram, but we can have one more over here, maybe Q01. So we can have Q0. Okay. So sorry, not Q0, Q bar for A. Okay. So we'll draw that after this. So okay. So let's just walk through this signal diagram over here, and let's just complete this over here, right? So after that, this flip-flop is just going to turn off, not doing anything over here, not doing anything over here until it sees the next trigger. So it's just going to keep this state. Whatever happens, it's just going to keep the state until it sees the next trigger over here. Okay, so the next trigger over here, this flip-flop is just going to turn on again, and it's going to see what mode is this in. So the mode is still the same. It is still in toggle mode. So toggle mode means that it's going to take whatever input that you have over here. So whatever value that you have over here, it's going to flip that. So from 1, it flips to 0. So that is how you get a 0 over here. From 1, it becomes a 0. And then it's going to keep that way, keep the same value at the output until it meets the next trigger. The next trigger happened at this point. And then it's going to flip that again. Okay, it's going to flip that again until it meets the next trigger. It's going to flip that again. Okay, so that is how we get the timing diagram for QA. Okay, and now how do you get the timing diagram for QB then? Okay, so for QB, take a look at QB. This QB will only get the trigger from QA bar. So it doesn't get the trigger directly from the source of this clock, but it gets triggered by the output of the first flip-flop. So that's why over here I'm trying to draw this output of the first flip-flop over here. So the output of the first flip-flop is just the opposite of what we have over here in QA. So this is QA, so QA bar. So over here we have 0, right? So in the beginning it will be inverted like 1. Then it goes down over here, and then this part it becomes 1, and then this part is going to be 0 like that, and then like it's going to be 1 over here, and then it's going to be the inverted version. Okay, inverted version of QA over here. So then once we have this QA bar, now we can try to compute. So the output over here, it gets this flip-flop only turns on if you have a rising edge. So the first rising edge happens when you have it over here, right? So this rising edge, take a look at that. This Q bar is given to the clock, and the first rising edge happens at this point. So in the beginning, everything is we assume to be reset, remember, for QB, and everything is going to be the same until it meets a trigger point. A trigger point only happens at this point of time. Okay, so this point it gets a trigger, and once it triggers, it's just going to toggle. It becomes 1. Okay, and after that, it's going to keep it the same way until it gets another trigger. So the next trigger happens like over here. Okay, you see, the next trigger happens over here, and then after it's got this trigger again, so this flip-flop is going to turn on, and it's going to flip it again. It's going to flip that value again. That's how I get this QB output over here. Okay, so take note at how different is it. The first flip-flop gets triggered very often because this clock signal is very high frequency. Okay, but the second flip-flop triggers less often. Okay, so because it only triggers if you have any kind of output coming from the first flip-flop. So it gets triggered less often compared to the first flip-flop. All right, so if you were to put it into this table, so you would notice something. So initially everything is 0, 0. So initially everything is 0, 0 over here. Okay, so at the first trigger, okay, things change over here. So at this point, things change. Let's take a look. What change over here? Initially, it's all 0, 0. Okay, and what changes next after the first trigger is this is still 0, and QA becomes 1. Okay, so QB is 0, QA becomes 1. That is the first trigger. Okay, after the first trigger, it becomes this one, Q01. Now, after the second trigger, which is over here, what happens? Okay, so then it counts, something happens again, and this one becomes 0, 0, and it becomes 1. Okay, QA becomes 0, QB becomes 1. Okay, now after the third trigger, which is over here, and this one becomes 1, and then this one is also 1. And then after the fourth trigger, which is over here, it becomes 0, becomes 0. Okay, so I hope that you're beginning to see the trend over here. So initially we start with 0, 0, and then we become 0, 1, then we become 1, 0, 1, 0 over here, okay, 1, 0, and then we have 1, 1, okay, so 0, 0, 0, 1, 1, 0, and then over here we have 1, 1, and then after that we are back to 0, 0, which is the last state over here. So do you notice what's going on over here? This is, if we consider this two output together, it is actually performing a counting up function, right? Exactly. So it's 0, 0, you count up to 0, 1, and then you count up again to the next output, 1, 0, and then you count up again, and then after you're done with the 1, 1, and then it goes back to this state 0, 0. So this is also called the recycle state. Okay. All right. So this is the basic function of a ripple counter, of an asynchronous counter. That is how it works. This is how it is connected. Right? Any question on this counter so far? Right? That is how you take a complicated, like it looks complicated, but actually it is very simple if you separate it. If you dissect it into its small component, it is that easy to understand. This is basically what an asynchronous counter does, right? So, and in this case, it's 2 bits. So if you add one more counter to that, it becomes a more bits. Let's take a look at another one. All right. So over here we have the same counter like just now, but we added one more over here. Okay, we added one more flip-flop by the end. Now that makes it a 3 bits counter. Okay, 3 bits counter. If you take a look really at the output, if you combine all this output, Q2, Q1, and Q0, okay, this is what you will get. So it counts from 0, 0, 0, and then after that it becomes 001, 010, and so on and so forth until the last recycle state. It goes back to 000. Okay, and this timing diagram is exactly the same. We produce it. How to produce this timing diagram is exactly the same that how in what we did in the last slide. Okay, so I hope you guys can work this out together. Right, so in this case, I'm trying to show you guys that this is a 3-bit asynchronous counter. So the only changes we did was adding this flip-flop. And what happens if you add more flip-flop to that? Like you can increase to 4-bit counter, 5-bit counter, 6-bit counter, and so on and so forth, right? Just by adding the flip-flop, and nothing fancy at all over there. Okay, so that is how ripple counter works. That is how asynchronous counter works. All right, so let's take a look at. We're done with asynchronous counter, right? It's that simple, right? Let's take a look at how does synchronous counter different. So I will give you a preview of what a synchronous counter is, and I really hope that you guys can take what I say in the class and explore what is a synchronous counter. Right, let's take a look at that. So the major difference between a binary ripple counter and a binary synchronous counter is the way the clock is connected. So this is an example of a synchronous counter. Synchronous counter. So this is a 3 bits counter. So how do I know 3 bits? So take a look how many flip-flops. 1 flip-flop, 2 flip-flops, 3 flip-flop. Okay, 3 flip-flops gives you 3 bits counter. All right, so now let's take a look at, let's just try to dissect this counter again. So what is the major difference? The major difference is at the source of the clock. Okay, source of the clock. Over here, source of the clock, source of the clock. So in a ripple counter, what happens is that the first flip-flop gets the clock from the second flip-flop gets the input from this one, right? From the first guy. But that doesn't happen over here. In this counter, in this synchronous counter, all the clocks of all flip-flops, they are connected to a single source. That is the major difference. So if you see a circuit that is like this, you know this is synchronous counter. All right, and the way the inputs are connected is also slightly different. Like if you take a look over here, okay, J and K, okay, J and K1, okay, no problem with that, J and K, okay, K, J, okay, K and J. All right, so the first flip-flop over here goes to the J and K of the second flip-flop. Okay, that is for this case. And now, next we see that there's even strange things over here. So the output of this third flip-flop is there's some kind of an AND gate over here, and this AND gate takes the output of Q1, a Q0, which is here, and Q1, which is coming here. And it goes to this AND gate and connected to that flip-flop. So how in the world do we know that this is the connection? So every synchronous counter with different function, you would have a different connection. So if you put the connection in this way, with an AND gate and is connected this way, it will perform counting up function. So it will perform counting up function. So it will count from 0, 0, 0, and then it goes to 0, 0, 1, 0, 1, 0, 0, 1, 1, and so forth, so on and so forth, right? So if you do, you can work this out using the timing diagram as well. Okay, so you can try this out. Initially, you can assume that they are all zeros, and you can connect this to a toggle mode. And so by giving a clock signal, so you have a clock signal, so you can work this timing diagram out just like how we did in the last slide. And then you have Q, 0, you have Q1, and you have Q2. So what you'll find in this timing diagram is that the counter starts from 0, 0, 0, and then it counts up every time it gets triggered. It goes one value up, one value up, and so on and so forth until it reaches the last value. It goes back to 0. All right. So what I want you to do is to find out how do we design synchronous counter to do this function. This is your homework today. So in chapter 8, as I said, I give you the most freedom in chapter 8. So I am not going to ask you to submit. I'm not going to ask you to complete this quiz, complete that quiz. No more quizzes in chapter 8. No more assignments in chapter 8. So I want you to be completely accountable by yourself. I am not going to check even on you because I know you guys know what is good for you. I know you guys know if you want to learn, you got to just go out and work it out yourself, right? So I don't wish our interaction to be like me, you know, keep on pestering you guys. Oh, do this, do that, like forcing you guys to do this. No, that's not the way to learn, guys. Trust me. You guys, the only way to learn is for you guys to work this example out by yourself on a piece of paper. Or if you don't do that, you can just watch a couple of tutorial videos and try to work this, at least mentally work this out. That is the best way to learn. And I am giving you guys this opportunity in this chapter for synchronous counter. It's just one subtopic of this chapter. So homework today, go back and find out how do you design this thing, how it ends up as, how do you know, how do we design a synchronous counter? In this case, it's 3-bit synchronous counter that performs this, right? That is how, that is what I want you guys to do, right? So this one is another slide, another addition to that. Is still a synchronous counter, but this time it's 4 bits. So as I've told you guys just now, if you want to make 3 bits into 4 bits, all we need to do is you just continue adding one more flip-flop at the end, and it becomes a 4-bit, 5-bit, and so on, right? Right. Just that's the difference. It counts from, this time it counts from 0000 up to 1111, and then it goes into recycle mode. Right. So that is what I want you guys to do today. That is to find out how to design binary asynchronous counter that goes up and goes down, and find out also how to design a binary synchronous counter that goes up and go down. Okay, so how do you do this research? As I've told you in the last class, one very effective strategy is go to Google search for these keywords: synchronous counter digital logic tutorial. You get a ton of result over there. Choose the best 3, choose the top 3, and take a look. You don't worry if you don't understand it. Just take a look. Come on, just take a look. Don't worry if you don't understand it. Just browse through the top 3 websites. That's first step. Second step, go to YouTube, search the same keyword, look at the top 3 videos with the most views. That is my strategy. Every time I'm trying to learn something new, I tell you, I use this strategy. I can learn anything I want, like literally anything I want, right? So I really hope that you guys can adopt this strategy also, not only for this class, not only for this topic, but you can do this to any topic in your life, like really. I hope you guys can realize this. This is what I'm trying to educate you guys on. I'm not trying to teach you guys how to do digital logic, how to do K-map, how to do algebra. Like you can easily learn that if you take what I'm trying to say away. I'm trying to educate you guys on how to use all the resources out there. And once you master how to use these resources, like the sky is your limit, guys. The sky is your limit. You can literally do anything you want with the knowledge that's out there. Majority of people don't know this, but this is another one try. This is one last time I'm gonna give you guys this research assignment. I really hope you guys do try this out. And that is all for our class today. And I would like to give a preview on what's going to happen in the next class. So this will be the end of topic 8. Topic 8 is very simple. We only have asynchronous counter, and we only have the next one is synchronous counter. We've just covered asynchronous counter just now, ripple counter, and I really hope you guys can do this research assignment on synchronous counter. And on Thursday, what's going to happen is that we are not going to have the usual class, but on Thursday, I am going to have a briefing. So the briefing will be what's going to happen for your final. So as you guys know, in my class, I don't really believe in final exam, to be honest with you. I believe that final exam is a poor way of evaluating whether you get something or not out of this course. So that's why I don't have final exam for my class, because I believe that you guys learn better by doing. You guys learn better by building something. That is what I genuinely believe in. So for this class, we are going to have, instead of final class exam, we are going to have a final class project instead. And this project is going to carry 40%. And I'm going to give you guys a briefing on Thursday's class. Okay, so I already have the slides ready over here. If you guys are curious, you can go through this slide and you can watch this video today if you want. The slides will be up after this class ends. And on Thursday, I am going to brief you guys on how to do this project, what this project is all about, and what the submission is all about, and how do we how do you do well in this project. So on Thursday class is an important class for this project. So do attend this class if you can. Right? If you cannot, then as usual, the recording will still be there, and you can always catch up with the recording. All right. So that one we talk about on Thursday, and that will be the end of our class today, guys. This is officially the last class of the semester, and this will be your last attendance. Yeah, on Thursday we still have attendance, but this will be the last attendance for any lecture for this semester. So if you came in late, do feel free to scan in your attendance. And if you have any questions, you can stay back. I'll be happy to answer any of your questions if you have. All right, guys. I wish you guys all the best, and I'll see you guys again on Thursday morning. All right, take care.
Thank you, sir.
Thank you, sir.
Thank you so much,
Thank you,
sir.
sir.
All right, take care, everyone.